All right, so in this video, I want to talk about wavefront sets. I'm just going to give their definition and some motivation for why we care about wavefront sets. So first, I want to recall some intuition from harmonic analysis. So let's say I have some sheet music. Actually, let's not even go here yet. Let's say I have a distribution U. U is a distribution. And for simplicity, let's just say it's a distribution on R, the real numbers. And so I have, so what is this thing? I mean, it looks like a smooth function of compact support, at least locally. All right, I mean, everything is locally of compact support. So it locally looks like it looks like a smooth function up to some small error term, right? But I mean, at least locally, this thing. Locally, this thing has a Fourier transform. So if you cut it off, you get a Fourier transform. You get something that has a Fourier transform. And so you can talk about the frequencies of this thing, at least once you've localized it. And so one way you could specify a distribution is to say, maybe, so this is a really badly drawn bass clef. Maybe here, it looks like we have a quarter note, and then we have a much lower quarter note, and then we have a half note, and then this is forte, and let's just put two half notes on top of each other. This one's piano, this one's pianissimo, this is also forte. Okay. So why did I draw this picture? So this specifies a distribution. I mean, the volume specifies the amplitude of each of the waves that make up the distribution. So here this is high frequency. So it's high frequency, so and it's loud. So this looks like this, and then after some time, after 1 unit of time, it becomes much lower, so it slows down, but still very large amplitude. And then here, it's actually a superposition of two waves. So I'm not going to try to draw that because that's hard, but the point is that at this point it becomes it's much quieter, right? Now this is overdetermined. We cannot just write down the frequency and the time, or we cannot write down all of the frequencies in each of their amplitudes of a distribution at every time. I mean, that would violate Heisenberg's uncertainty principle. But it is helpful to think of a distribution not as something on R, but as a map from R across R. So this is time, and this is frequency. To R, this is amplitude. Essentially, this is saying that at any time, so let's say at this time, it looks like a superposition of waves, and so each wave has an associated, or each wave has some frequency and an associated amplitude, and so the function U eats a time and it eats a wave, and it eats a frequency, and it says what part of the distribution U is oscillating at this frequency. What amplitude does that part have? And again, this is totally just intuition, because you can't actually do this because of Heisenberg's uncertainty principle. But it's going to be something that we're going to use in a little bit. Because what is a wavefront set? It's going to be something that's going to tell us about the function, and it's both in position and in frequency. I'm mixing up time and position here, and so the key point is going to be that if I act on, so A is a pseudodifferential operator, and U is a distribution, then AU, so pseudodifferential operator of symbol A, and U is a distribution, then AU is like A x c, U of x c, where again we're thinking of this thing not as a distribution, but as something that depends on both time, as a function that eats time and frequency and spits out amplitudes, and this thing is just a function multiplication. Because symbols, by definition, eat time and amplitude, or sorry, eat time and frequency, and spit out amplitude. And so this is not actually true. This is false. Because, again, Heisenberg's uncertainty principle says that symbols commute, pseudodifferential operators don't commute, and so this cannot possibly be valid in any sense, but it's at least true to lower order. So that's going to be a very useful intuition in 1 second. So to define the wavefront set, we start by recalling the notion of support of a distribution. So the support of a distribution is it's the intersection of so phi u equals 0, phi is a compactly supported function of the set phi equals 0. So essentially, I look at all the test functions and I see if the test function kills u, then I want to add this this phi equals 0 term. And so because this is clearly a closed set, this is also a closed set. But in pseudodifferential calculus, we're interested in singularities, where u is not equal to c infinity. And so what's kind of genius is that we can just say phi of u equals 0 modulo c infinity, or in other words, phi of u is an element of c infinity, and this is called the singular support. The singular support of a distribution u is just the set of points where u cannot be represented by a smooth function in some neighborhood of that point. So obviously the singular support of delta equals 0, and the singular support of a Brownian motion, for example, is all of R. Because this thing is not differentiable anywhere, so in particular it's not smooth anywhere. And I guess the idea of this distribution, or the idea here is that we're cutting off in time, but we also want to, the idea of wavefront set is let's also cut off in frequency. And, well, how are we going to do that? We want to replace these functions, multiplication by a smooth function of compact support, by in time by one of multiplication of a smooth against a smooth function that's regular in time and frequency. And those are symbols, but we don't want to multiply by the symbol. We want to apply the pseudodifferential operator. So what we're going to do is we're going to say that this is like, so the wavefront set of u is like AU is an element of C infinity, where A ranges over this space L naught, and in some sense A is non-zero. So what is L naught? So L naught is by definition space of psi DOs of order 0 and proper support. So being of proper support is sort of analogous to being of compact support. Remember that these things cannot possibly have we cannot possibly be compactly supported. Again, by Pauli-Wiener theory or whatever, you can't have something that's compactly supported in time and in frequency. And so proper support is really the right definition to use. Being of order 0 in particular means that they're not unbounded, so they're bounded on L2, for example. So they're not going to generate any new singularities. And so what the hell is this? What is the set on which a pseudodifferential operator is non-zero? That's kind of a nonsensical, it's not a nonsensical concept, but it's the wrong thing to use. So that's going to be something called the characteristic set of the pseudodifferential operator. Characteristic set of A is by definition. Also, there's a really nasty thunderstorm outside, so apologies if there's any like crazy background noise going on. So the characteristic set is the set of all xc in the cotangent bundle of our time space x minus 0. The origin is not interesting. So these are all the cotangent spaces with their origins removed, such that the limit as t goes to infinity, still on my screen, yeah, it is. of A x p c equals 0, where A is principal for A. So let's unpack this definition a little. So remember that a symbol is principal. I mean, this quantizes to capital A to top order, and the reason why we do this is in general, X is a smooth manifold, and so in general, without some sort of like Riemannian like Levi-Civita connection or something, asking what the symbol of a pseudodifferential operator is just nonsense. But the principal symbol is defined invariantly, I mean, for this definition, if the principal symbol goes to 0, then any other symbol is going to go to 0. So we might as well just take it to be the principal symbol, because the principal symbol dominates. Because the principal symbol dominates everything anyway. So this is well defined based on choice of representative of the principal symbol. And the fact that t is going to infinity here, in particular, means that this is a conic set. So like if lambda is if lambda is greater than 0 and xc is in the characteristic set of A, then lambda c is in the characteristic set of A, because this lambda just gets absorbed into the t. So characteristic set of A is conic. This kind of motivates why we care about cone bundles. I mean, if you read Hormander's paper, he cares a lot about cone bundles. I have to admit that it doesn't actually really motivate it though, because like the fibers of the cotangent bundle minus 0, or rather the fibers of the characteristic set are not all isomorphic to each other. Locally, the characteristic set does not look like X cross a cone. So this is clearly not a fiber bundle. But I guess the intuition, I mean, I don't really know. This is one of those great mysteries of life. Is why does Hormander worry so much about cone bundles? That's okay though. So once we have the characteristic set, we can talk about the wavefront set. The characteristic set is kind of like where these things are non-zero, just on the grounds that like what we're interested in is if this thing is 0 at infinity. So the wavefront set is going to be a conic set. It's going to be closed. Again, intersection of closed conic sets is a closed conic set. In general, like I said, it is not a cone bundle, but I think maybe you're supposed to think of it as kind of like a cone bundle. And it is going to be the set of points where if we cut it off in space and frequency to those points, if we cut it off in space and frequency to a neighborhood of those points, or rather a conic neighborhood of those points, then the function u becomes c infinity. Okay, so that's like our main definition. And I do have another thing that kind of puzzles me besides the cone bundle thing, which is why is this defined as a subset? So this is clearly a subset of the cotangent bundle of x minus 0, but why not mod out by r plus? Because the real numbers plus infinity clearly acts on the cotangent bundle minus 0 just by rescaling, and the fact that this is conic means that in particular the action preserves the wavefront set. So the data of a wavefront set consists of points in x with like a direction of momentum attached, but we don't remember anything about the length of the momentum vector, just the direction. So I don't really know what to say about that. Why is this not a subset? Why not make the wavefront set a subset of the cosphere bundle? I don't know what to say about that. Okay. and this is probably the way you should think about it actually, is just forget this conic set stuff, just think about it as a subset of the cosphere bundle. Yeah, it's a little unfortunate. So the wavefront set is a subset of the cosphere bundle, and it has a nice little characterization. I'm going to cheat and use this quotient again. So let's say P is the projection that defines the cosphere bundle. And then and U is a distribution on X. Again, X is just some C infinity manifold. Then the push forward of the wavefront set of U is the singular support of U. And so basically this first condition says that a point is in the wavefront set if well, first of all, that implies that its projection is a point is in the wavefront set if its projection, or that implies that its projection to the original manifold, the point is already bad there. So in order for something to be in the wavefront set, so xc is in the wavefront set if and only if U is bad at X and bad at C. So in particular, it has to be bad at X. And if it's bad at some C over X, then it's bad at X. And so for every C in the singular support of X, the fiber of the wavefront set at X is the quotient X here. The fiber at some point X in the singular support is the quotient of the largest cone in the cotangent bundle such that for every phi, or this is a test function. For every test function phi, with p of x non-zero, there's n greater than 0 such that for every c in the cone, CW hat C, it grows at least as fast as C to the minus n. And so this bracket here is, of course, the Japanese angle bracket. So this just means that near infinity, this is just equal to teak C. And this means there's an implied constant. Basically, this whole thing means that near infinity, this grows faster than teak C to the minus n. So basically, this rules out the possibility of you looking sort of like a Schwartz function. I mean, something is locally smooth if and only if it's locally Schwartz. So this is or it's smooth if and only if it's locally Schwartz. So this is kind of like the condition for not being Schwartz. So in particular, it's not locally smooth in a neighborhood of X. Specifically, and specifically, it's not smooth in the direction C. And I will omit the proof of this. It's in Hormander's paper. I just want to give 2 examples of wavefront sets. Let me just let this sit for a second, and I will give 2 examples of wavefront sets. Okay. Oh gosh, the thunderstorm's getting really crazy. Give me 1 sec. Yeah, the weather's nuts outside. Okay. So example. So this is kind of like the first motivating example. Let's say let U be an open subset of the C infinity manifold X. And the point is that its boundary should be a smooth submanifold. So maybe X is like R3, and U is some ball, and then its boundary Y is like a sphere, for example. Okay. And let little u be the indicator function of the open set. And so it's pretty natural to think just what should this wavefront set be? Well, so this thing is not very interesting away from the ball. Like over here, this is not very interesting because here it's just identically 0. And in here, inside the ball, it's identically 1, so it's also not very interesting there. So its singular support is clearly the sphere. I mean, everywhere away from the sphere, it's locally constant. Or actually, it's just straight constant, actually. Or, sorry. Everywhere away from the sphere, it's locally constant, and if we restrict to one of the connected components, it becomes constant. So it's not interesting there, and the singular support, so the singular support of U equals Y, okay? But in what directions does this thing fail to be smooth? Well, if I just take like a tangent vector to Y, for example, and I differentiate along the tangent vector, nothing bad happens, right? Like it is what it is. So to define so this suggests that we need to look at like the normal bundle to Y. But wait a second, we don't have a choice of Riemannian metric, so what the hell does the normal bundle correspond to in the cotangent bundle of X? Well, here's just a definition. The conormal bundle to a closed embedding. So I have a closed embedding of manifolds. This means that Y can be viewed as a closed submanifold of X. And the conormal bundle is just the set of XC, or sorry, maybe I should say Y eta, since this is the Y. Y eta in T star of X. Well, first of all, it's a bundle on Y, so little y better be in Y. And for every V in T T Y Y, eta kills T. So what this so the tangent bundle of Y is perfectly well defined, and the fact that this is a closed embedding means that the tangent bundle of Y is a subbundle of X. That's perfectly fine. Or sorry, a subbundle of the tangent bundle of X. So this tangent bundle of Y sits in the tangent bundle of X. And the point is that if we have a tangent vector to Y, so here's our tangent vector to Y, then the conormal bundle should annihilate, or the conormal, the fiber of the conormal bundle at this point should annihilate this. So it's sort of like it's orthogonal to it. So it sort of looks like guys over here. Noting, of course, that orthogonality is not defined in this setting, but that's what the conormal bundle is. So if you're thinking to yourself, well, the conormal bundle is closed, it's conic. I mean, it's a vector bundle, so of course it's conic. maybe, and it certainly seems like this thing should be singular in the conormal bundle. So maybe we think that the wavefront set of U is the conormal bundle of Y. That would certainly be a reasonable thing to think, and it's true. But we have to prove it. So first of all, this level of generality is totally unnecessary because this is a smooth manifold. Y is a smooth manifold. So without loss of generality, X is Rn, Y is Rn minus 1, and U is a half space. So without loss of generality, Y is like a plane. Okay, this is a plane. And so if Y is a plane, then U of X and Y, let's say, and let's call this like little y. Okay, this is a bad choice of terminology now because now. Okay, let me. Okay, well, whatever. Let's just run with it. Little y equals 0 is the equation that cuts out capital Y. Okay, then this is just the Heaviside function in the y. And so if we take Schwarz cutoffs, so by the Stone-Weierstrass theorem, we can always just assume that the Schwarz cutoff is a tensor product. Okay. Then UF hat of C and eta. Well, how does Fourier transform interact with tensor products? This turns into G hat of C, HH hat of eta. All right, so if C is non-zero, then we get decay because G hat is a Schwarz function, and HH hat of eta. Well, what's the Fourier transform? So this is like H hat of eta because little h is just a cutoff. Well, the Fourier transform of the Heaviside function near infinity is just 1 over eta. So this thing is like G hat of C over eta, and so if C is non-zero, the fact that G hat is a Schwarz function means that this just dies. But if C is 0 and we take eta to infinity by itself, then this is like 1 over eta, and definition of wavefront set means that definition of wavefront set means that thing, or not the definition, but rather the theorem we proved about it, or didn't prove. The theorem that we did not prove about the wavefront set means that if C is this fixed while eta goes to infinity, then we get the blowup, which tells us that that point is in the wavefront set. Okay, so that gives us a proof of this claim right here. That the wavefront set of a indicator function is the conormal bundle of the boundary. Okay. So a lot of hand waving there, but I mean, you can pretty easily fill in the details as an exercise. And so another example, which motivates the name wavefront set, is to say so first of all, the wavefront set of the delta function is t star 0 of Rn minus the origin. Why is this? It's the fiber of the cotangent bundle at 0 minus its origin. Why is that? Well, first of all, the singular support of this thing is clearly just 0, so its fiber is so the wavefront set is contained over the fiber of the cotangent bundle at 0. And the delta function is invariant under rotations. So, actually, more importantly, the Fourier transform of the delta function. The Fourier transform of the delta function is just 1. It's clearly invariant under rotations. So it doesn't matter what direction you're pointing. You don't get any decay in any direction. And in particular, you don't get like the Schwartz decay that you need to prove that something is not in the wavefront set. Okay. So why is that interesting? Suppose that box u equals 0 is. So what does this mean? This is the wave operator. So let's suppose that u is a solution to the wave equation, whose Cauchy problem is posed with initial position delta and initial velocity 0, or initial. I guess initial position is the right word, delta and initial velocity 0. And let's say, I call this D actually, that's not very important. And let's say we're just looking at this forwards in time Cauchy problem, we're not looking backwards in time. And the support of U is a subset of this light cone. So this is in time, and this is in space. And this is just a general fact about finite propagation speeds, but of the wave equation. We haven't used the wavefront set yet. And so if D is 3, 5, 7, etc., then in fact U is the surface measure on this cone with a singularity of 0, obviously. But if D is like 2, 4, 6, 8, etc., so this is, okay, I should make it clear that this is RD, and this is R. If D is like 2, 4, 6, 8, etc., then we only have a weak Huygens principle, and we get a bunch of junk inside the cone, possibly. I mean, depending on, I mean, I haven't actually said this for delta, but in general, we might get a bunch of junk inside the cone. Like if you throw a rock into a pool of water, then the waves keep emanating even after the initial impulse, because the surface of water is two-dimensional. So then I get a bunch of junk in here on top of the waves out here, the surface measure out here. And so crudely, the reason that this is true. So crudely, the reason that this is true is that the wavefront set of delta, so here's 0. The wavefront set consists of momenta based at 0, and they point in all directions. They point in all directions evenly. So in particular, in particular, they don't privilege any particular direction, and the wave equation should propagate the singular support of U in the direction of the wavefront set, and that's every direction. This is the Poor-Mander's famous propagation of singularities theorem in a very trivial special case, which is that the singular support moves in the direction that the wavefront set's momenta tell it to move, according to Hamiltonian dynamics, which in this case just means the wave equation. And so this kind of tells you why this thing should be called the wavefront set, because I mean this cone is the wavefront of U, of this wave. It is the point at which the support of the wave breaks down and goes to 0. So yeah, that's about it. That's all I want to say about that.